the Web3 sustainability loop is an idea put out by Ocean Protocol.
Hmm.
Trent McConaughey writes about this, and it's this idea of sort of manage how to manage an economy, and it's inspired by the corporation and the government, these kind of models that we've seen over the past 100 years, and it's basically monetary policy. It's like money should be minted and allocated effectively. So it's this difference between effective allocation of money. It's like if money is printed and not efficiently allocated, then that is inflation. That's what causes inflation. And if money is printed and allocated efficiently, then that is growth. So this is the key thing to nail down, right? Is like it's not necessarily about how many tokens we're making, but it's really about how they're distributed, how they're issued, and what they go towards. And if they go towards productive means, then this production should be able to produce enough sort of inflows. And then this is where it's been really nice tracking the one hive honey model because it's really about inflows, outflows, and production. And that's it. That's the recipe. It's like if you can take the tokens that are being minted and make stuff with them, fund the community, fund projects. I mean, exactly what we're doing here at the TEC with the hatch and the bonding curve and the proposals and this whole process, which I was sort of like lecturing some people last night about all this stuff, and I realized how many holes there are in my own knowledge. Like, I'm not even sure if what OneHive has with the common pool is that. Did they launch an augmented bonding curve? Is that what you would call that? No.
No, no, not at all. They just have issuance. Well, so they want to change it to dynamic issuance, where it has awareness of how much is in the funding pool versus the total supply. But they just have issuance pumping into the pool. They took out the bonding curve and they only have conviction building. And then they just print money. Currently, they just print money at a steady rate into the funding pool, and and really they print money and it goes in. I mean, it's like there's an issuance contract, and at any time someone wants to, they can push a button, and based off that time and the last time that button was pushed, money will be minted and sent to the funding.
Well, that's a manual process. It's not automatic.
It can't. So the automated part is the quantification of how much can be
Mm.
set at any moment.
Mm.
Uh, but unfortunately, the EVM requires an external account to take action on contracts
Mm-hmm.
for actions to occur. So it's like the best tech doesn't always win. Let's just put it that way. Ethereum has a lot of problems, man. There's a
Mm.
lot of really annoying technical like hacks to
Mm-hmm.
make it do all the cool stuff we want it to do.
Mm-hmm.
And one of the big things is you just can't have a contract just like at a certain time do something. You could have a bot that has an external key,
Mm.
and then that bot, a Web2 bot, just like triggers, it has gas
Mm.
money and it triggers something. You can do that, but you can't have the contract do it.
Interesting. Yeah, I never thought about that.
I know.
But yeah, overall, Boson's been great, and it's a lot of work to just keep up with everything that's happening. But I think their vision is wonderful, and the founders are great. They have good mindsets, and I think there's going to be a lot of collaboration between the TEC and Boson. Ah, I see Angela just joined.
Hello.
Hi, Angela. Welcome.
Hi, guys.
Yeah.
Thanks
Hi.
for the reminder, Mark. I almost forget about it. And since I was assuming it was last week, but it's great to have this presentation today.
Yeah, it's a
Just in time.
two-part series. This one.
Ah, therefore. So for session number one was last week.
Yeah.
Okay. Great. I'll
Awesome.
switch off video.
Hey, welcome, Mark.
Thanks.
So I'll just go over the ritual to begin. So I'll go ahead and share my screen and just remind everyone. So take a look at the TEC Labs, um, cool, TEC Labs channel, and you'll see in the pinned messages a link to the Notion workspace. And from there, go ahead and open up the attendance sheet. And pick your favorite emoji for the day. Let's see.
So obviously I should know what happens with this sheet, but I don't. Can you give me a glimpse?
So nothing happens with the sheet yet. It's just a fun project, really, to see what kind of emojis people enjoy. But
Okay.
then it's available. I think the idea is we could do a. I think we could do a lab sometime. Well, there's not that much
Mhm.
rich data here, other than I guess the social media platforms or operating systems. Maybe we could do something with that. But the idea was just to generate a data set
Mhm.
of the TEC lab that maybe one day we can actually go ahead and analyze and do some data science on this data set itself. But
Cool.
nothing's been done yet. But it's nice to track this attendance, so we could definitely do a POAP or something along those lines.
Yeah.
Yeah.
Oh, nice.
Yeah, it's nice to see. I really like the operating system distribution to see what everyone's using.
Mhm. Just checking.
All right, so good. And if there's any questions, anyone can just let us know. And the lab worksheet. So if you check the calendar, and today is February 19th. Nice. Okay, so we have this workspace here available, and I'll hand it over to you, Mark.
Well, thanks, Ig, or should I call you Sean? What do you prefer?
Yeah, you can call me Ig.
Ig means me in Dutch.
Oh, that's interesting. I didn't know that.
uh, or ich in German.
Okay.
Right, Angela? Yeah, sure. Today we're going to talk about our reinforcement learning agent in the loop of energy web. Last lab I talked about how we went on with the energy web submission. As a matter of fact, we are already collaborating on that together with Lior from the Data DAO guys, and he reached out to join basically join efforts in order to maybe get something up and running with Energy Web and Data DAO together. We're in the process of setting up a 2-page or something, which I will share in due time. For this lab, I think we need to go a bit again through the intro of the token spice cadCAD migration, just a short overview of what we discussed last time, and then head over to the reinforcement learning stuff. But maybe, Sean, you can give a quick intro about the reinforcement learning agents you did for us for the TE Academy. Um, with your Notion Notion page, this I think, to get everyone up to speed. What are we talking about when we talk about reinforcement learning engines?
Sure. Good idea. Okay, so I'll link this in the I think I'll just stick. There's lots of good resources in last week's Notion page in the lab space here. So I'm just going to keep building on this one. Let's see. Do I have permissions to edit? Seems like I'm not
Oh,
able to edit this.
maybe that's my fault. Let's see.
I think it's just a Notion thing. Okay, I'm in now. I
Oh,
had I
okay.
had to click a button. Okay, so in this page from last week, I'll link to that there. I'll also just drop it in the TEC Labs channel. Yeah, this was a fun presentation that I gave in the Ocean Protocol study group about the potential of combining reinforcement learning frameworks with token engineering frameworks, particularly Token Spice. And so I gave some background to reinforcement learning. Maybe I'll sort of go through this briefly. I talk about this primary framework slash library that is available. It's produced by OpenAI, and they have a library called OpenAI Gym, which creates these. So back up a little bit. What is reinforcement learning? It's this. It's two standard data structures. We have an agent and we have an environment. An agent has an action space that it can operate in this environment. And when you're thinking about token engineering, this is really useful. It's a nice matching because the action space are all the contract functions. That's how, when you think about the EVM, the state of the blockchain in the world, all the things that we can do are essentially the functions that are defined in the contracts or the protocol itself. So we can interact with the protocol itself. We can do things like deploy contracts, or once those contracts are deployed, we can interact with them. And so the action space, I like to actually show people this. If we go Open Zeppelin, maybe here. So if you don't know Open Zeppelin, it's a standard audited secure contracts. And if we go into contracts and token, then ERC20, then this is an awesome resource. And if we check out the interface, then we have all the functions available on the standard ERC20. And so if we were making an agent in a token engineering simulation where maybe there's only ERC20s deployed, then this would actually be the action space for the agent to interact with the contracts. And some of these are sort of read-only, where they have this view keyword. Then we can sort of inspect the state of the contract, like getting the balance of an account on these ERC20 tokens. And then some actions actually change the state, like transferring an amount of tokens to a recipient. So you can think of these as a vector, like a list in Python. So you would have a list of actions. You could encode each action with a number, 1, 2, 3, 4, 5, 6. And you could have a basic agent that like randomly samples. So you could have a uniform distribution, like rolling a dice from 1 to 6. And maybe this agent takes a random action. And you could have thousands of these agents that just continuously take random actions. And then you'd be able to see what are all the wallets of these agents, how many tokens do they have, are they transferring these tokens, and you'd get to see how this system plays out, maybe if every agent was just acting randomly. And that's usually your baseline when running and deploying AI algorithms, is like, what would happen if we had a completely random policy? And once you get that working, then you can start to actually use the sort of reinforcement learning algorithms that will change the policy over time based off feedback from the environment. So that's the action space. So each agent has the opportunity to take an action. An action affects the environment. So like we said, some of these, if you do a transfer, then you're actually changing the state of maybe the EVM in this case. And then the agent gets in return some reward. So if the agent takes a series of actions that result in, maybe a reward function is maximize my number of tokens that I hold in my wallet. So the more tokens you have, the more reward the agent's going to get. And then again, the agent's going to get to observe the environment. So this is encoded similar to the action space. We have a vector, and the observation space is going to be maybe a vector or a matrix. The observation space could simply be what's the balance of my wallet. So we could encode a very simple ERC20 interacting agent where it's taking random actions on an ERC20 token, and after every action it takes, it gets to see what its balance is. So it's going, and if the reward is to maximize its balance, then it's going to learn quickly to stop transferring funds. So this would be a very simple implementation of a reinforcement learning agent in a token engineering simulation or a token economy. And the purpose of this presentation was to give this background on reinforcement learning, and then also talk about the opportunities with Token Spice. Because it connects directly to the Ethereum virtual machine, we can actually execute these. We can do exactly what I was just describing. We can define the action space of an agent to be actual smart contract interactions, and then we can run these agents through our simulations to test our smart contracts and the token ecosystem. And so what I did as an example is I have here is all the agents defined in Token Spice to test the Ocean protocol ecosystem and do some tokenomics analysis and verification and simulation to get these sort of results where we can say, well, what's the annual revenue of the DAO over time? So we have monthly Ocean DAO income, Ocean minted and burned, and this is interesting. Griff and I were just talking about One Hive and the Honey issuance before the call, so I'm not sure exactly their issuance rate, but Trent found that you can do sort of a linear issuance. You just print the same amount of tokens over time, I say monthly, and on the opposite side of that, you could do like an exponential decay in your token issuance. So this is what we see in Bitcoin. And then Trent found, he says, by far the optimal is a sort of ratcheted exponential. So you do this ratcheting, he calls it. And I don't quite know the precise definition of what ratcheting is, but you can clearly see it in this graph here, where it's this, I think it's like a pseudo-manual token minting process over time in the early days, and then an exponential decay over time. And Trent mentions that in the simulations that they run for Ocean Protocol, this is by far the best issuance policy. And how they modeled this in the simulator is that actually the agent, they have an agent that is a minting agent. So this agent gets to decide how tokens are minted over time, and they just had three pre-programmed options. They had the linear, the exponential decay, and the ratcheted. And so they found these results that the ratcheted did the best. But this agent itself could be a reinforcement learning policy that you could train over simulations. So typically in RL, we have this idea of an episode, and many RL problems are trained on video games. And so one episode is maybe the agent will play through an entire level of a game, and then at the end, it'll have its total reward, and then there'll be some credit assignment part of the algorithm that decides at each step of that game what was the reward, what was the credit attribution of the action that the agent took in various states at various points in time. So we could have a minter agent that we could run like hundreds or thousands of simulations, and we could have an RL algorithm that sort of optimizes this minting process over time. So this is a overview of this RL process, and then here I have a coded up example. I took one of the agents and showcased how we could modify this and augment this to have some reinforcement learning. And I'm just wondering, Mark, how am I doing? Do you want to jump in at this point, or? Should I? Mark, if you're there, you're on mute.
Yeah, sorry. Yeah, this is a good point to jump in. Yeah, as a matter of fact, I looked at your example first because there are not so many examples about reinforcement environments besides the let's say the standard gym environments like the carpo and this kind of stuff. So it was really a journey in how to set up custom environments, because this is what we need for our reinforcement learning agents. As you can see here in this picture, Sean is showing here that he makes use of a model. It's given into the initialization function of the agent, of the protocol speculator agent. You give him a model, and this model is being trained beforehand, I guess. And this model will predict the next action to take. If you scroll down a bit further, Sean.
I don't see that I import. Did I forget to import the model? The actual.
Yeah, yeah.
Okay, yeah.
So the model somewhere has to be. That's no problem there, because we suppose that there is a model available, a trained model available for this agent. And you see then in the take step function, that's a normal token spice simulation step function. You see that you first calculate the reward, you append this reward, and then you do an action. And this action is being predicted by the model. So the model itself has a function, it's called predict. This is a function I really needed to flesh out and to see where does this predict function is coming from. And I think this is a nice opportunity to share my screen in how my journey went this far.
Awesome.
Okay, I will share this one. Let's see. I think you see my entire screen now. Is that correct?
Yep.
Okay. Okay. Can you see my VS Code stuff?
No, we're seeing Discord.
I think I forgot to share the whole screen. Okay. Here, yeah. Okay. Now you should see the code screen, correct?
Yeah.
No?
That's right.
Yeah, all right. Yeah, so to pick up where we left last week, we talked about the energy web agents. Quick refresher, energy web agents, tokenized power balancing. We need to power the balance within a microgrid of energy consumers and producers. So we use the energy web origin toolkit for that. And we need some sort of external interaction and also the ocean market to do that. Well, basically, this is a high-level overview of the synergy I presumed for my submission. On the one hand, you have Energy Web with where you can register power devices, and you have some sort of marketplace over there that you can sell and buy power. On the other hand, you have the data marketplace of Ocean, the Ocean market, where you can publish and consume data sets with data token pools. So the neat thing would be if we can pack the registered metered data of a power device in Energy Web, we pack that to a data token pool in order to stake on that. And the idea is that staker agents will stake on a data token pool packed to a power device if that power device is behaving in a right manner, which means that it's correctly producing results according to what they predicted. And here's the thing, the prediction itself has also some value, because when a power device prediction about his power producing profile is correct, then you would say, okay, this power producing device is reliable. So we can predict what the outcome will be, what the power production will be in the next hour or the next day, maybe. And of course, you can have all sorts of staker agents around that are going to predict how that power producing device will behave in the future for the next hour or the next day. So it's quite a dynamic system. We talked about that last week. I briefly introduced the concept. So the idea is, how about staking staking on these data token pools in order to have this prediction or a signal, because if you stake on the data token pool, that's a signal that that data token pool is worth something. So the idea of signaling staking behavior, we take that to the next level. We say if you stake on a data token pool of a power producing device, actually you signal that this power producing device is behaving in the right manner. And this, of course, has some value in the whole decentralized energy system as a whole. Okay, that's the business side of it. Now the technical side. Last week I said, okay, we have some energy web agents. I fleshed it out in a separate directory. So first of all, of course, in the cadCAD migration, I just copied and pasted all the agents of the token spice environment to this directory. We still need some agent to start the simulation up, so that these are the agents I kept in the correct directory. But next to it, I fleshed out a new directory, Energy Web Agents, EW Agents. And on this part, I will flesh out the real Energy Web Agents implementations. So we talked a bit about the pool agents. We talked about publisher agents. The publisher agent is the agent that is really responsible for publishing data token pools. So this is basically the agent that is really is interacting with the Ocean marketplace. And after his action of publishing a data token pool, we have an Energy Web pool agent, which is basically the manager of the data token pool. And we can interact with the pool agent when we want to stake on it. That is being done by the Energy Web Staker agent. I tweaked a bit about his staking behavior. At this moment, I am going to simulate a randomized staker. That means that once in a while it stakes on the data token pool, and the other, in 50% of the cases it will stake, and in the other 50% of the cases it will unstake. And there is some sort of sophistication in the how he will stake or unstake. That's in this function to select a pool to stake and unstake. It's really a really simple strategy. He is going to sort the pools that are being staked upon, and he will stake on a pool that has let's say the fewest oceans staked on, and on the other way around, it will unstake on a pool that has the most oceans staked on. So it's basically it's a randomized behavior, but we need some sort of dynamics into the simulation. So this is what I modeled. You can tweak around and let's say alter the magic numbers. That was some sort of, maybe Sean, you can elaborate on this a bit, what a magic number is.
Yeah, so I mentioned this last time. This is a nice aspect of the token spice framework, is that we leave these. So in general, software engineering, a magic number is a bad thing. You don't want to have any magic numbers. It's when you just have a floating int or float in your code somewhere, and usually people don't know what it means or why it's there. So you want to abstract those out into sort of a configuration space where they have variable names, and you can get all these magic numbers all in one place in this configuration file that then gets loaded into your system. But Trent inverted this principle. He actually leaves all these magic numbers in the engine, in the system itself. And so to really augment your experiments, you need to go through the source code and find all these magic numbers and get to tweak them appropriately. And this is kind of unorthodox from like a software engineering practice, but from a simulations practice, it makes a lot of sense because it reduces the abstractions. We're not abstracting everything away. We're actually leaving the knobs in the system where they make the most sense, right? Directly on the policies themselves, on the agents themselves, on the environment themselves. And it ends up working quite nicely because it does reduce these like abstractions that you have to follow with all these imports and sort of separating the components. It leaves the components together with their parameters that can be tuned. And at any point, you could take these out. You could find all the magic numbers, and you could put them in one configuration file and then import them. And maybe I could see that happening when people are applying token spice to very large scale simulations, large scale environments. But as of now, it works great. It makes it really easy to just modify the code on the fly.
Yeah. So as you see here, I put some print statements just for debugging purposes or just to show what's happening. I will start out a simulation now, so you can see what's happening during the simulation. So when the simulation is starting up, it starts to publish 2 data token pools to stake on. And you see that we have some energy web publishers staking and unstaking also. And later on, we can see that energy web stakers are also going to stake on it. So we have an energy web staker, David, who is going to stake on that. And an energy web staker, Moselle. And once in a while, every 3 hours, new data token pools are going to be published. So basically, this is the setup for the reinforcement learning agent to have some sort of couple of data token pools to stake on according to some sort of strategic behavior, of course. And I will let it run for a while. You can play with it. I will commit this also to the repo, so you can fork it or clone it. And you can play around with it yourself. But basically, this is the idea. I will shut it down for a moment.
So, Mark, we have 30 minutes. Do you think we should try to get this reinforcement learning going?
Yeah, I'm going to that.
Awesome.
No problem. So what you need to remind is, okay, we have some sort of pool staked on. We have the energy web pool 0 until 3, 4 maybe. And we have some ocean staked on. And you see, we had some strategic behavior of the staker agent, but also of the publisher agent. I forgot to mention that is showing some sort of dynamics within the ocean being staked. So this number is going to change. Okay, so not to keep you waiting too long, now we head over to the reinforcement learning stuff. Actually, that's in here. So I will shut this down. First of all, if we want to go and implement some sort of reinforcement learning agent within this simulation, I'll try to mimic what Sean has shown you before. So we need some sort, I call it the energy web optimizer agent. He is going to be the reinforcement learning agent that is staking or is showing some sort of strategic staking behavior. And I tweaked a bit around with the action spaces, and here you can already see that it's being already quite complicated. Sean, you mentioned, okay, the action space is a tuple. I played around with it, but actually I couldn't get it working. So I resided to a multi-discrete action space, which is also fine. So basically these two things, the action space and the observation space, are the things you need to take care of in the first place. So what do I mean by a multi-discrete space? We have multi-discrete means you have an array of discrete spaces. So we have, for instance, 3 distinct action types, 4 distinct energy web pools, and 4 distinct maybe staking percentages. We could model this differently, but for the sake of simplicity, I kept it for 4 discrete values. And as Sean mentioned, the action types are just plain integers. 0 for I do nothing, 1 I stake, 2 I unstake. And where do I stake or unstake? That's the second action space parameter. One of the 5 pools. Okay, I presume we have 5 pools to stake on or to unstake from. The observation space, on the other hand, that's what I showed. Why I showed the simulation is we need to take care of how on what kind of pool will the optimizer agent stake on or unstake from, and that is dependent on how good or how bad the pool is behaving or the pool is being staked upon. So it needs basically the amounts of ocean being staked on the pool to get some sense of, is this pool good to stake on or bad to stake on? So I have to unstake from that. A really simple strategic behavior. I'm not sure if that's really working, but this is the idea I had in the first place to model my reinforcement learning agent. And I did that here in a sort of testing environment. I really spent a lot of time setting this up. As I mentioned, there are not a lot of examples in the Stablebaselines of, let's say, custom environments, because you need, for this optimizer agent, you need some sort of customized environment, and you need to set that up quite by yourself. There is some documentation in the Stablebaselines, but it's not really that fleshed out, in my opinion. So it really took me a long time to set this up. But then, as you can see, you can look at this line here. And this is, of course, this resembles the action space and the observation space I just talked about in the optimizer agent. These are the same. So this is the setup. We have an episode length. Sean talked about you train in episodes. Well, basically these are all kinds of this kind of stuff is quite standard. I also set a balance. So in order to stake on, you need to have some ocean, of course, or another cryptocurrency. And you need to have a reset function. Basically, this you can look up in the documentation of the Stablebaselines customized environment section. And what I did is I also played around with some sort of a chaos monkey. I have some sort of a randomized action that is, let's say, is influencing the state. But first of all, let's see how we define the state after a step function. And basically I say, well, I take the action space. The first parameter of the action space is, of course, do I do something or not? Do I do nothing, stake or unstake? That's the first parameter, the 0. The second parameter, the 1, is, of course, which pool I need to stake on. So if you imagine that the state, the observation space, is actually the state, and this is a box space, and we say it has a shape of 5. It means that we have 5 values in it, and they're continuously growing from 0 to 100. But I noticed that's not a real threshold in this Stablebaselines. What I also did is put a gradient in it. What do I mean by that? I need to have some sort of idea of, okay, how should that strategic behavior look like? And how I modeled it is to have some sort of a gradient of the observation state of all the staked pools. So basically the state or the observation space is being modeled by 5 pools, 5 energy web pools, and we fill this up with an amount of 10 ocean to start with. And of course, if you are going to stake on it or unstake, these values are going to change. And the manner or let's say the rate of change, I put in the gradient. So basically, if this state is growing from 10 to 11, let's say we have 10 ocean, and in the next step, it's 11 ocean. I take the gradient of that increment, and that gradient I will take to let's say to calculate the reward. So if the gradient is big, so if there's a big change in it, and that could be you could see that as a signal of, hey, this pool is behaving correctly because the staking is really increasing fast. You could say, okay, this is something I need to stake on because this pool currently has the best holds the best cards. So the reward is a function of this gradient. Also, if you unstake from it, of course, if the gradient is negative, so people are taking their stake away, they're unstaking, it's a signal of, oh, this pool is behaving badly, I need to get out of it. So basically, it's the other way around. The reward is a negative if you unstake on it, but the gradient is positive. So then you have a negative reward. But of course, if the gradient is negative, you have a positive reward. So you do the right thing. Maybe this is not making sense, Sean. This is not my cup of tea. It's more your cup of tea. But basically, this is my idea of how to model the reward function. Any comments on that, Sean?
Yeah, I'm definitely following the intuition, and it seems to make a lot of sense to me. And I'm sure I mean, this is really a space for creativity in modeling the reward function. But for me, yeah, I would just run this. It's always good to have a baseline, hence the name Stablebaselines, right? And see what behavior emerges out of this kind of reward function. And yeah, well, you notice this about reinforcement learning. There's a lot of sort of rationalizing that happens because there is, in the very middle of what's going on, there's a black box, right? At the end of the day, we have an RL algorithm, and takes a lot of time and energy to sit down and read the paper behind it and understand all the math and really think about what's happening. So we have this sort of black box in the middle, and on one end we put our intuition behind the reward function, and then on the other end we run the experiment and get the results. And then there's this sort of rationalizing that happens between what we expected given the reward function and then the actual results that are output, and often there's surprises. So
yeah. So I noticed
yeah.
because I played around with this all day. I should mention that because I couldn't get it right, and maybe that's the whole idea of playing around with it. You know, I will just start it up. You can see it here in the control. What's happening? So now it's training based on this reward function and the observation space. It's training the agent for 25,000 steps. I guess I took that number just from an example. I guess that's okay. And I modeled the first 10 steps. So basically what I did is actually this is the outcome of the training step. A mean reward of negative, so doesn't show too much confidence. But I need to let's see, say something about what kind of algorithm I used for training this. I used a PPO2 model. Doesn't know what that means, but I took your PPO algorithm out of your Notion page, Sean. So I guess this was some sort of a right algorithm to take, but there are several. And so you can do as you like. I had some difficulties in saving and loading the model. He complains about vectorizing environments. This is the stuff I really need to dig into further. But then when I could use the model without saving it, just to go through it and let's see, um, do some 10 steps of predictions. So as you can look here, this is something you might noticed out of the presentation Sean gave. This is the actual prediction of the action, what to take for what observation. So the observations are here. That's the state, and it takes some actions according to the gradient. And if the gradient is positive for some pool he needs to stake on, then he will stake on. So if you see here, the action space in step 1 means 0 is no action taken on pool 1 with a 50% staking amount. Next one is action 2 is unstake on pool 1 with a 25% staking amount. Or we take away 25% of the ocean. So basically, this is how I put the simulation and put together the stuff. And what you can see is that I try to accumulate the reward and see what's happening with the reward, and it's really not really happening for 10 steps, but maybe if we can increase this with 100. And sorry, I have to train it again, but because I didn't flesh it out.
So you were
Let's see
having
what happened then.
so Mark, you're having an issue with trying to save the model, was that right?
Yeah, because it's complaining about vectorized environments. You need to have, if you want to save it and load it again. Yeah,
Yeah, I've seen
this is stuff
this.
I
I've seen this
really need to.
before. It's somewhat
Yeah.
familiar. There's like a wrapping and unwrapping. I'm just looking at an old example that I had ran on a project. I'm just trying to get it running kind of in the background here. So I don't mean to take away too much attention, but I do remember there's some key concepts in here that I had dealt with. So I'll see if I can get this running. Oh, that might work.
Yeah. So basically, what I did, I tried to tweak some parameters here in the model right here. So I tweaked around a bit with the reward function. Let's see. Yeah, I also said, okay, if you are out of balance, if your amount of ocean is getting too low, you're also penalized by subtracting the reward with 1. So basically, you can. I did the most of the modeling I did within the reward function, but you also can do something, of course, about the observation space. I have a real simple observation space now of, 5. I'm looking at 5 energy web pools, but in reality there could be hundreds of thousands of these things, and the reinforcement learning agent just needs to pick one in order to maximize its reward. So you can model basically these are the tuning parameters, I would say, of your reinforcement learning agent. So the action space and the observation space and the reward function, of course. I think you need to spend a lot of time tweaking around the reward function, but you don't. As I recall, Sean, you shouldn't be too specific about the reward function, I recall, because otherwise you are going to give the agents too many clues. And you need to have him figure it out by himself, right?
Yeah, exactly. Because essentially, a reinforcement learning algorithm is a search algorithm through a very large search space. It's like we're generating a function that maps actions to no, it maps observations to actions, and these we wanna do a comprehensive search of that search space of that possible function, and if we pre-program in the reward function to be too specific, then we're sort of constraining the search of all possible behaviors, of all possible policies, to something that we're kind of imposing our own bias on. And maybe sometimes we do want to do that to search like a local area or a specific area of policies. But in general, reinforcement learning is going to shine when it has this sort of organic search through a diverse policy space. So it is a yeah. It's this is one of the key aspects that we have at our disposal, is like how we engineer the reward function. So there is this balance of like not being too specific, but and so one way you might want to do this is you could code up, you could kind of save this. You could have a whole, maybe even a whole file, or you could just make various reward functions. You could have a whole collection of them, and then in the actual reward function here, you could just sort of call one of your collection of reward functions. So we could do like this A/B kind of testing. But what I'm thinking about here, off the bat, is the training, because how much training are we running on this? How many episodes, for example?
25,000 steps, but the episodes are 100 time steps. I think I modeled 100. Let's see. Yeah, here. So basically the episode length is 100. Should I increase that?
So is this for each episode we're running a simulation that is 100 steps?
Yeah.
Yeah, so that's an interesting point to consider. So I think in the token spice modeling, it comes with this idea that one time step is 1 day. Was that right, or was it a month? I mean, it doesn't actually change the...
Yeah, 1 day, I think.
Yeah, I think it's
Yeah.
1 day. So we can think we're running this simulation for 100 days. So we're theorizing that we have these agents, and they can stake and unstake on these data pools, and we're giving them 100 days to do so, and getting some summation of rewards over those 100 days. And then we're running them on, was it 25,000 episodes?
Yeah. Yeah, well, total time steps. I'm not sure if that's 25,000 episodes or time steps, because then you need to divide that by 100 maybe. I haven't figured that out yet.
Oh, okay. What are we doing here? Okay, so let's see.
So basically, I'm taking here the episode length here in the implementation of the class. Let's see here. So we have an episode length of standard 20, and it's done. If we have the episode length here, then it's done, of course. So you just train for 100 time steps each episode, I think.
20.
No, okay, yeah.
Or-
If I don't give them this
Okay,
parameter,
you're
but
overriding
I
it
do
with 100.
here. I do,
Ah.
well, we can try it without. Let's see what's happening.
So that'll be 20. So what we want to do is to get some insights into this. My mind always goes to visualizations. So I would want to run this multiple times with varying episode lengths. So maybe
Yeah.
20, and then 100, and then 500, and then 1000, and sort of plot the performance, or maybe the final reward, against how many time steps we take. And then you can start to get this
Yeah.
idea of, okay, are more time steps increasing the performance?
Yeah. So I see the main reward is a bit better, I think, now. So maybe if you can, let's see, put 10 or 20. Yeah.
Can I ask a question in the meantime?
Sure.
I was wondering, since you're starting from scratch here with not that much heuristics on the pools, the pool sizes, number of actors, number of agents, and so on. Is there a best practice in the process of optimization to track all the various parameters you're changing here and then comparing the results? Since I think there's kind of the danger to go all over the place and don't understand the results anymore, or are not that sharp on interpretations. You know what I mean?
Yeah, I know what you mean. I'll jump in on that one. So it's this idea that there's so many ways to set up these experiments.
Mm.
What's the observation space of the agents? And so it's like we could run experiment after experiment. We could tweak things. We could go through this sort of rabbit hole of running so many experiments, and then at the end of the day, well, how do we track all of our progress? How do we remember that it was important for the agents to track the number of other agents or the number of pools or the total staked, like all these different ways that we
Search
can.
elsewhere,
Mhm.
exactly. Or
Mhm.
do it vice versa. I don't know. Create a roadmap and I don't know, best practice. Follow your roadmap um, at least for 10 variations until you change your roadmap, whatever. I don't
Mhm.
know if there are any kinds of frameworks or best practices established.
Yeah, I don't know of any particular, not like a framework that I can point to, but I think it's the general scientific method, and I think what we've been seeing in the Gitcoin, with the Gitcoin methodology with Danilo, I really enjoy how he starts all his sessions with the HackMD file, with
Yeah,
everything laid out. You know, the experiment is designed, and then coded, and then ran, and then there's this review process. So yeah. Sort of taking a step back and outlining the expectations of the observation space and the reward function and the agents, and then running those experiments and comparing the results. So I think we do see this when you look at the literature in reinforcement learning. There is this process. There's also sort of a more programmatic way, which is like a grid search, you know. So there are algorithms like hyper or meta algorithms that you can throw on top of your reinforcement learning algorithm that will strategically search the parameter space. You can define how this is a lot like what cadCAD does with A/B testing in the system parameters. But instead of just A/B testing, there's algorithms that will actually search through the hyperparameter space, and there's often the class of algorithms that get applied to this is evolutionary, inspired by evolution. So you can set up multiple reinforcement learning experiments um, with differing hyperparameters, and then combine the results in a way that is similar to that of like evolutionary traits. So you can randomly scramble. So you could take your observation space, or you could have your set of parameters that you can be included in your observation space, and you can do a random selection over them, or maybe you could do 100 random selections, and then you could run all of these reinforcement learning simulations and sort of select for the top 10, and then take maybe an average between their hyperparameters. So there's this sort of automated approach, and then there's the methodology approach, and I think both are very important because of the complexity, the nature of the complexity of these problems. It's so important to document along the way. This is speaking from experience, how many thousands of hours I've,
sure.
had the most beautiful experiment results, and then after all night of hacking, I completely forget how I set it up, or what I had to begin with. So, yeah, the
Yeah.
documentation process is really important.
Yeah, cool. Thanks for sharing. That's interesting that you can even run optimization on your experiments parameters. Cool.
Yeah, I'll give a shout out. There's a really cool Python library. It's called Teapot, and it's for genetic algorithms applied to hyperparameter optimization. Really interesting.
Ah, cool. Maybe you can share a link.
Sure, I'll drop a link. Um, yeah, good stuff, Mark. So it's awesome that you got this running. You've got this reinforcement learning
Eventually.
setup going inside of cadCAD, inside of Token Spice. This is quite the feat for a hacker. Very inspiring. And
Well, actually, I haven't brought it into Token Spice yet because I was, of course, still training this stuff. And the next step is, of course, once you have a good model, trying to get it into your optimizer agent. But that's next level.
yeah, I'm wondering if we should continue these lab sessions, the series. We can do some chat offline. There's nothing really rigid blocked. I have a couple ideas of slots to be filled with the labs, like some more work with OneHive, but it's pretty flexible. So I think maybe now that we have this foundation and that you have here, maybe we could do a whole lab session where we actually just program on this and try different reward functions and maybe do some of this experiment methodology that we've been learning from the Gitcoin track.
Yeah, it would be nice. As an observant.
Mm-hmm. Mm-hmm. I'm happy to open
No,
this
no.
up. And,
Yeah,
yeah.
we
No,
could
no,
at least
I will
pseudo
hack
code.
together with you.
What was that, Angela?
I was saying we could at least pseudo code. I mean,
Yeah.
doesn't lack creativity, I
Yeah,
guess.
sure.
Yep. Yep. That's important too. Yeah. Okay, everyone, that's the hour. So, Mark, thank you so much for this amazing two-part series. I think you've blown everyone's minds. You've put in Token Spice inside of cadCAD, inside of Stablebaselines. It's quite amazing, and I think it would be awesome to continue this work in the labs. So we'll figure out how we can set that up. And yeah, and thanks everyone for coming, and have a wonderful weekend.
Okay, thank you.
Amazing. Thanks for sharing. Have a great
Okay,
weekend, guys. Bye.
bye bye.
Bye bye.
Always great. Thank you guys.
Awesome.
Bye, everyone.